Okay guys, welcome to the third video on substitution and elimination reaction. This is going to be going over nucleophiles and bases. Part of being able to understand this topic is understanding what nucleophiles and bases are, as well as determining what is a strong nucleophile and a weak nucleophile and strong base and weak base. Okay, there's a couple factors to go into that, but it's a relatively intuitive topic, relatively intuitive factor, all right? So first, what's a nucleophile? A nucleophile is something that can attack, right? So we've seen OCH3 minus, and it can attack, like, let's say, a carbocation, right? And so that's what a nucleophile would have been, right? Nucleophiles usually have high electron density. Electrons are what actually attack. And a base, well, a base is just something that grabs a proton, okay? So that's the difference between a nucleophile and a base. Now, nucleophiles can also act as bases, but we'll get into that a little bit later. Okay, so there are a couple factors to consider when talking about nucleophiles and bases, right? So the first thing that really predominates is charge. This is the first thing that should really be looked at, okay? If you have a negative charge, you are much more nucleophilic, okay? So in other words, OH minus is more nucleophilic than H2O. It has higher electron density. 3 lone pairs on that oxygen versus 2 on here. Same if I had, like, let's say, NH2 minus versus NH3. Okay? And so we can see that those more electrons are more nucleophilic. So this is a better nucleophile than this, and then the same reason here. Okay, so that's the role of charge. Pretty straightforward. Another thing to look at is electronegativity. Okay, so we know that electronegativity increases as we go to the upper right of the periodic table, right? And so remember how for REO, when we look comparing acidity or like the conjugate bases, if we were in the same row, we looked at electronegativity. If we were in the same column, well, we have to look at the size. Here it's kind of similar. So atoms in the same row, right? As we go to the right, we increase electronegativity, right? So I'm going to put these 4 nucleophiles. Right, so I took carbon, nitrogen, oxygen, and fluorine. So this is going to the right of the periodic table. We know that as we go to the right, electronegativity increases, right? That means that atom has a much higher affinity for electrons, right? And so how does this correlate to being a good nucleophile, right? Well, think of it this way. As we go to the right, we're increasing our electronegativity, but we're also decreasing the size, right? Size goes down. So we're concentrating electrons in a much smaller area. We don't like that, right? Those electrons will repel. So that means as we go to the right, your nucleophilic ability goes down. Okay, so that means this is the carbon with the minus charge is a better nucleophile, which is better than nitrogen, oxygen, and the fluorine. Okay. If we are in the same column, right, we have to look at solvent. Okay. So what is the solvent, right? And what is it actually? What role does it have? So there are 2 categories for the solvent: polar protic, polar aprotic. Polar protic solvents, key thing is the pro, or prot, right? We've heard of protons. So this is similar in that we have hydrogens, right? But most importantly, we have hydrogen bonding, right? Remember that intermolecular force? So that means if I have a solvent like H2O, CH3OH, ETOH, which is an ethyl group instead of a methyl group, right? Or something with nitrogen and hydrogens connected to it, right? Those are polar product. They are capable of hydrogen bonding, okay? So these things are capable of hydrogen bonding. Polar A product do not. No H bonding, okay? We don't have hydrogen bonding for polar A product. Some examples of a polar A product solvent would be something like, if my general ideas or rule is if it's got a weird name, it's polar A product. DMF, DMS, DMSO, acetone. Okay? So those would all be something that's a polar A product solvent. Okay? So that's just kind of an easy way to remember it. That doesn't require as much of, but again, feel free to put some examples that you've seen on your index card, right? I mean, it's there for you, might as well. Might as well definitely use it. All right? And so those are the two types of solvents, but how does that actually do anything in terms of tells us how good nucleophiles are, right? Because that's what that's what we're focusing on. Okay? So let's look at polar product first. So if we look at iodine here, remember we were saying we look at solvent when we're comparing things in the same column. Br minus, Cl minus, F minus, right? So what happens if I put fluorine in a polar product solvent? So I take fluorine with its negative charge and put it in water, let's say. So I have water. Now let me draw that better. Okay, so we have water here, right? It's surrounded by water molecules. Right? So remember, hydrogen bonds form between hydrogen and an electronegative atom, usually oxygen, nitrogen, fluorine, right? So you just put fluorine with a negative charge surrounded by its electrons into water, right? Those hydrogens are super attracted to that negative charge. So what we are going to get is these hydrogens attracted to that fluorine, right? Because remember, fluorine's got that super big negative charge, so it's going to be partially negative. The oxygens in water are partially negative compared to the hydrogens. So that means a hydrogen has a partial positive charge. So that partial positive is attracted to that partial negative on the fluorine, or that full-blown negative charge, actually, right? So look at what's going on here. We put that one fluorine in there, and it was surrounded by water molecules. That's something called solvation, right? And so how can I be a good nucleophile if I was instantly caged by these water molecules? Well, you can't, right? Think about it. You put that fluorine in there to react in whatever we have, yet it's instantly surrounded by water. So, well, we can't do it now. It's going to stop it, right? So this is the whole idea of how polar product solvents work, is they use hydrogen bonding to, the hydrogen bonding acts on electronegative atoms, right, and kind of hinders them from moving around, right? So if we're ordering the halogens I wrote, fluorine would be the worst one. It's got a very concentrated negative charge. It's small and the most electronegative. So this is going to be the worst nucleophile. That means that we're going to increase as we move down the column. Okay? So we can say that in a polar product solvent, nucleophilicity increases down the column, right? So this, the context I'm thinking of in this question would be, they're going to ask you, out of these three halogens, which would be the better nucleophile in, let's say, DMSO, or in H2O. So you now have to think, okay, that's H2O is polar protic, and everything is in the same column. So I have to look at the effects of the solvent on the nucleophile, okay? And so we know that nucleophilicity will increase going downward. So that's the trend for polar protic. How about polar aprotic? Right, so this is again a DMF acetone. Another one could be something like, actually no, yeah, I think that's all you'd really ever see. So this has the opposite trend. All right, this has the complete opposite trend. So fluorine is better than chlorine, is better than bromine, better than iodine. Okay. Now this reason isn't as clear, but in this case we don't have hydrogen bonding to hinder our nucleophiles, right? And in reality, what it is that nucleophilicity is actually very close related to basicity. Okay, good nucleophiles can also be good bases. Okay, and so it's just easier to remember, in my opinion, that polar protic, we increase nucleophilicity going downward. Polar aprotic is the complete opposite, right? And so I said it correlates to basicity. So just to quickly explain what I was saying, you take HI versus HCl, two acids, right? HI is a stronger acid than HCl because if you look at the conjugate base, I with a minus charge would be larger and can spread out the electrons more than Cl minus, right? Because we have here iodine, negative charge, electrons spread out everywhere, versus chlorine, negative charge, spread out but just not as much. Okay, so if iodine is the more stable conjugate base, it's stable, so it won't really react. Chlorine, on the other hand, is still considered a little bit relatively stable, but it's going to be a little bit of a stronger base because it's not as stable as iodine. It's not able to spread out the negative charge as much. So we said HI is the stronger acid, which means I minus is the weaker base, which also means more stable. So if you're stable, you don't really want to react. This is going to be a stronger base, more reactive. And so it's more reactive, so our nucleophilicity will be better. So we're going to have increase in nucleophilic ability. Okay? So that's how nucleophilicity works in terms of the solvent. Now, one more thing we need to look at is something called steric hindrance. Steric. I'm just going to write sterics. Okay? Steric hindrance revolves around the idea that large substituents can get in the way of certain things, right? Because compounds can be bulky, and that can start screwing stuff up. Okay? So compare H3C O minus, right? So that's just an oxygen bound to that methyl, versus this compound right here. So now it's an ethyl group, right? So essentially I branch that methyl out by one more carbon, versus this last compound right here, right? So the one on the left had one carbon bound to our O minus. The one in the middle has this carbon and it branched out one. And this one has a carbon branched out to 1, 2, 3 methyls, right? So think of it this way. A nucleophile is an attacker, right? Nucleophiles have to attack our compound. So that means it has to get into our compound and get really up close. So imagine I have a carbocation, and this is going to come in and attack that carbon. It has to physically get in there, right? So it is going to be much easier for a nucleophile to get in there if the nucleophile itself is small, right? That's logically speaking, smaller things can get in easier. It's going to be much harder for something large to get in there, right? Because it gets in the way of this. Because if I have, like, let's say 3 methyls now off of that, off of this carbon right here. Let me redraw it. Off of this carbon, if I had 3 methyls off of it, now as that nucleophile tries to move in, you can see that the groups on our compound itself, they stick out as well. And the methyls on our nucleophile are going to kind of clash with it. It's not going to really work, right? And so we have to consider that as well, okay? And so how would I show this? So we know that the one on the left is small. The one in the middle is a little bit bigger. The one on the right is really big, right? And the one on the right is a very common one you'll see. It's called tert butoxide, all right? And so I'm going to try to show it to you guys here. So imagine I had this carbocation. Each of these carbons is a methyl, right? So all these carbons have hydrogens coming out of them. Now we're reacting with our tert butoxide. O with down to carbon 3 methyls, right? So how would I draw this out? So here's our carbon, 1 methyl, 2 methyls, and a 3rd methyl, right? Now imagine trying to fit this guy, right, into this. Oh, and I should give it a negative charge. So imagine trying to fit this really big, bulky group into our compound. Imagine this. It's coming in. I got to get real up close. And now look, the methyl near the top is colliding with the methyl over on the upright on the top part of our carbocation, and the lower methyl is going to interact with that bottom right here. So you can see I'm coming in, it gets really close, and now these methyls are hitting each other, these methyls are hitting each other, right? Well, it's going to make it really difficult. And so we can say that the bulkier our nucleophile is, the worse of a nucleophile it will be. All right, so that's another thing to consider. So out of these 3 that I drew, this is the worst nucleophile. This would have been the best. Okay, so I just talked about nucleophiles the entire time. What about bases? Okay, so nucleophilicity correlates very closely with basicity. So in terms of charge, right, the better nucleophile is OH minus. It's also the better base, because remember, we know that negative charges prefer to take hydrogens too. So in this case, it is a good nucleophile and a good base, right? Same deal for electronegativity, right? What do you call it? The atom that will prefer to grab the hydrogen will also be actually a good nucleophile, okay? So that relationship works too. That's why nitrogen right here versus the OH minus. Nitrogen is a good nucleophile, right? Because you see it's more to the left than OH. It's also a good base, right? Because NH2 minus with a negative charge is very, very basic. It doesn't like to exist that way, okay? So versus OH minus, which is basic, but not as basic as NH2 minus, okay? And so yeah, so that whole idea still works too. Actually, this should be written as not NH2 minus. Sorry. Because yeah. Oh no, sorry, no, we're fine because there's 2 1 pairs here. Okay? And so, right, we can see that as our nucleophilicity increased to the left, so did our basicity, right? Just think of the carbon with that methyl. Have you ever seen a methyl with a negative charge, right? It's very rare. Carbon with a negative charge is very basic. So it's going to really quickly grab an H, right? So the same idea here. Now we talked about the solvents, right? We know that the polar A product correlates with basicity, so that isn't much of an issue, right? Usually the solvent isn't going to be too helpful in determining the basicity. That would be probably determined more with one of these, all right? So we mainly talked about good, I said good nucleophiles would be an OH minus, which also means that the bad nucleophile would be H2O. So another way we can say this is neutral usually means weak nucleophile. And also a weak base. All right, like I said, they go very closely together. All right. Now, so that should be as much of a problem. Usually, you'd be able to tell what's a good base and a good nucleophile. But what about this case? I have a Cl minus compared with Br minus. All right. Now, this is something you've already learned. Okay, so not everything is new. We build off of the topics. So they can ask you, what is the stronger base, right? What would act as a base? Well, chlorine is higher up in the periodic table. Br is lower. They're in the same column. Br minus is bigger, so it can stabilize the negative charge much better than chlorine can. So because it is stable the way it is happy to stay this way, right? Whereas Cl minus is not as happy, so it's going to be a little bit more unstable, which means more reactive. A strong base is considered reactive. Now, I'm not saying chlorine is a strong base, Cl minus, it's not, but it is stronger than Br minus. In fact, the halogens are considered not basic at all, really. But again, they could ask you to compare between them, right? So watch out for that. So halogens are good nucleophiles, weak bases, all right, except fluorine. Fluorine is not a good nucleophile. Not a good nucleophile. Didn't mean that. Fluorine is actually considered relatively basic compared to the other halogens. Okay, so definitely watch out for that. Whereas OH minus, it is both a good nucleophile and it is also a good base. Halogens, good nucleophiles, bad bases. All right, and then the trends hold for everything else. All right, with more practice, you'll be able to get these better. There are also other nucleophiles and bases that you will encounter that I have not discussed here. So, for example, Cn minus. All right, now just looking at it, you wouldn't really be able to tell if it's a good nucleophile or a good base. Right? There's no way you could really tell just by looking at it, but you will learn just with practice that Cn minus would be a good base. Sorry, good nucleophile, bad base. Okay? So, yeah. All right, and again, a lot of the stuff is with practice, and I'll show you a lot of example questions, come up with charts and stuff like that. So if anything in this video didn't make sense, please feel free to email me. Go to TA office hours, CLC. If you're watching this on YouTube, please feel free to comment. And like I said, do not get too caught up with all these factors, okay? Use your logical reasoning. Think of the charge. Think of your ARIO rules. They still hold. We don't just magically change something because it's a new topic. Everything builds off previous material, okay? So good luck, guys. I'll see you next video.